let's take a look at an example that ties everything together with both linear and quadratic regressions and doing some of them by hand. So we have some data below, and it represents the concentration of E. coli bacteria measured in a unit called colony forming units for 100 milliliters in a swimming area that's monitored after a storm. So essentially, we're just measuring how much E. coli is in a swimming area after so many hours. So 4 hours, 8 hours, 12 hours, up to 24 hours. We're going to find the equation of least squares line, and we're going to use the polyfit function. We're going to find the equation of the least squares parabola, and we're going to use both the polyfit function and the matrix method described above, and we're going to use Excel to help us out. We're going to create two scatter plots, one of which is going to be the linear scatter plot, the other one is going to be the quadratic scatter plot. And we're going to plot the data and the curves. We're going to compute some residuals for each of these. So we're going to plot the residual for 8 and 16. And then based on all of our observations, we're going to determine which one we believe to be a more effective representation of the data, whether it be linear or quadratic. So first thing we're going to do, let's go ahead and program or hard code the data into our MATLAB. So we're going to have X is 4, 8, 12, 16, 20, and 24. And Y is going to be equal to, now I'm going to flip back and forth, unfortunately, for this. So maybe I can pull one of these tricks real quick. And Y is going to be 1590, 1320, 1000, 900, 650, and 560. And we're going to get the least squares equation. So we're going to say P equals polyfit, X comma Y comma 1. All right, so that's the linear association. And let's say LS line is going to be equal to P1 times X, and I'm going to say X1, so it's different than this X data, plus P2. All right, and I'm going to define LS line to be a Sims, so Sims X1 as well as LS line. Right. And finally, we're going to say in fprintf that the equation of the least squares line is %s, and we're going to \n, and we're going to say that s is going to call ls line. All right. So in the same vein, what I'll do is I'll get the polynomial or the quadratic one as well. So I'm just going to say ls quad, and what I'm going to do is I'm just going to copy this code, and what we're going to do is we're going to change 1 to 2, and I'm going to call this, let's just call this Q, so that way it's not the same variable. And we're going to have, so we're going to have Q1 times, and I have to change this times, and we're going to say that's going to be multiplied by X squared. All right, and Q2 and then Q3. All right, so that should give us both of the equations for both the least squares line and the least squares quadratic. I'm going to call this ls quad as well. And let's just change this to ls quad. And this is the least squares parabola. All right, so let's go ahead and execute, see what we get out of this. All right, and this should be x1, which is probably why it's giving us a matrix instead of just the actual value. So let's run that again. All right, so here's our two equations. All right, now the hard part for us is being able to get the equation of the parabola by using the matrix method. All right, so it's easy to just use the polyfit function. That's what MATLAB likes to do. But for us, let's just go ahead and let's plug it into Excel. And you might remember our formula. And let's scroll back up a little bit. So for our formula, we need sum of x squared, n, x cubed, x4, y, xy, x squared y. So we're going to compute all of those. And we're just going to use Excel. So we need an x, we need a y, we need an x squared, we need an x cubed, we need an x to the fourth. not 44. And then we need an xy, and we need an x square y. All right. And remember our x data is 4, 8, 12, 16, 20, 24. And our y data, I'm going to see if I can do the same thing before where I minimize it and just kind of look at this. So 1590. All right. There we go. 1320, 1000, 900, 650, and 560. All right. And remember, what you do is you just take A2 and you're going to square it. And you're going to take A2 and you're going to cube it. And don't forget the equal sign, like I did. And we're going to take A2 and we're going to raise it to the fourth. And then we're going to take A2 times B2. And then finally, we're going to take C2, which is the x squared, times B2. All right. And what we're going to do is we're just going to highlight this data. All right. What I'm doing, by the way, is I'm just holding the shift key in and just hitting the arrow, the directional arrow on my keypad. And then I'm just going to drag this. And then finally, I'm going to get the sum of the first column. And similar to what we had before, so sum, I forgot equal sum. So equal sum, and then I'm just going to highlight this data, and I'm just going to drag this. And these are the numbers that we're going to throw into our matrix. All right, so let's hold on to those because those are important numbers. And now what we can do is we can program that into our matrix. All right, so now our matrix, if you look at the pattern, square, first order, and then n, which in this case is going to be 6 because there's 6 observations, cube, square, linear, fourth, cubic, square. So it just goes into, it starts out with square, and then it just kind of goes in descending order and then ascending according to polynomial terms. All right, so it shouldn't be too difficult for us to program this. So let's call A, and I'm going to bring this up, and hopefully we can just kind of look off of that. If it'll let me, it doesn't look like it's going to let me, so that's a bummer. I'll just drag it on my other screen. So A, we're going to start with the square for x. So that's going to be 1456, and then x, which is 84. And then we have 6 order pairs, and then we're going to put a semicolon. Okay, remember semicolon is for the next line. And then cube is 28224. And then we can just copy the 1456 and the 84. And then finally, our fourth power, 582400. And then our cubic, 28224, and then square is 1456. So that takes care of a larger matrix. The smaller matrix is going to be y, sum of y, which is 6020, semicolon, and then xy, which is 69760, and then finally x square y, 1066,880. All right, now we're hoping that A divide B, and I'm going to call that R, is going to give us the same thing as what we got the first time we used the polyfit. So in other words, this animal. All right, and I'm just going to execute it to see if we get any numbers that are even close, like a 1926 for the constant. So let's run that. All right, and we get 10 to the third, 1926. So if we bump this over 3 decimal points, 1926, it gives us what we want. So it looks good. So now let's just call this LS line 2 or LS quad 2. And that's going to be equal to, so it's going to be R11 times x1 square plus R21 times x1 plus R31. All right. And finally, we can just copy this and parabola using the matrices is, and I'm going to call this LS quad 2. All right, so let's see if we get the same thing. All right, so least squares parabola using polyfit is, okay, so now we have that differentiated. All right, and check this out. These two are exactly the same. So one of two things happened. Either we got extremely lucky or the method that we utilized works well. All right, so far so good. Next thing that we're asked to do is we are asked to, and we are asked to create two scatter plots, plot them side by side. All right, so we're going to have a subplot 1, 2, 1, and we are going to let x1 be equal to, now notice the lowest x is 4 and the highest x is 24. So we can use that trick where we have min x colon 0.01 colon max x. All right. And then we're going to plot x comma y as a scatter plot. And then we're going to hold. And then we are going to plot x1 versus ls line. And we're going to hold off. All right, and our x-axis or x label is going to be the time in hours. And the y label is going to be the concentration. And it was in that unit colonies per CFU. So colonies forming units. So CFU. All right. And finally, we're going to title this. This is going to be the time E. coli, time versus concentration, linear association, or we could just say linear regression. Okay. All right. Now the good news is we've just done all the hard work. Now let's just copy and paste this. And we're going to change this to 2. We're going to plot x1 versus ls quad. And then we are just going to change this to quadratic. All right. So let's give it a run. Let's see what happens. All right. So it might be, let's go back up here and try that and put a dot in here. All right. And it might be good if I just redefine each of these. So let me just redefine that right here. That way we're not doing anything weird. And I'm going to do the same thing with the least squares line. I'm just going to redefine that. I know we already found it, but let's just replot it just in case. All right, let's try it again. There we go. Okay, so here's our subplots. And they're both actually pretty decent fits. If you notice, like this point is kind of far off, not really far off actually, but it's further away than this point is. However, there's some trade-offs here because some of them are further. So for instance, like if we look at 16 and 16 here, the linear association is much better. All right, so looking at the scatter plots, there's there's some discrepancy between those. All right, so maybe the residuals might help us. All right, so, and I believe that's the next thing that we're asked to do, is that we are asked to be able to find the residuals for both models. All right, so remember, for a residual, and I'm just going to put this in parentheses, residual is equal to y actual minus y predicted. And the y predicted is found by substituting the x value back into the least squares line. All right, so I'm going to call this ls line 8, all right, because we are asked to find the residual at 8 and at 16. So I'm going to do it twice. I'm going to do it once for 8 and once for 16. So ls line 8 is going to be equal to, and what I'm going to do is I'm just going to take the least squares equation right here, and instead of x1, I'm just going to plug in 8. And I'm going to say residual, or ls line 8 is going to be equal to, we're going to take the original y value. So when x is 8, y is 1320. That's going to be 1320, which is the actual minus ls line 8. All right. And we're just going to do this again for quadratic. So I'm going to call this ls quad 8. And we're just going to copy the quadratic form or the quadratic regression. And I'm just going to plug in an 8 everywhere that I see x1. And I'm going to call this res quad 8. And that's going to be equal to 1320 minus ls quad 8. All right. And let's do 2f_f. So f_f, the residual at t equals 8 for the linear regression is %f, and we're going to call res line, so residual line 8, and we'll just do the same thing. And I spelled residual wrong for the quadratic regression is, and we're going to call this res quad. All right, so let's run this. And remember, the larger the residual, the more error. All right, so it looks like that there's more error in the quadratic regression at 8. And let's take a look at the graphs for these really quickly, just to verify that. So when t is equal to 8, all right, then this one's almost right on the line. This one's really good. All right, at 8, it's not too far off, but that data point is not really all that close compared to the other one. All right, so there's a little bit more error in the quadratic regression this time for the residual. Now let's do the exact same thing, except we're going to just change all the 8s to 16s, make it really nice and easy for us, including the variable names. All right, so just bear with me as I do this. All right, and I also have to change the 1320 as well to the original y value for when x is equal to 16. So just bear with me a moment as I change everything. And the only other thing I'd have to do is just be able to find what the original y value was. I think it was like 650 or something, but I'm not willing to guess. So it was 650. It was 900. Excuse me. All right, so just 900. I'm going to substitute that back in. So our y actual is 900. All right, so let's give it a run. All right, so now this time the linear association is almost perfect. All right, and the quadratic regression is pretty far off comparatively. All right, so almost triple of what the regression is for this one, so a lot more than that. So it's just much larger. So now the last part of this asked us to be able to do an analysis. So based on your observations for C and D, which of the two models would you believe to be better? At this point, we can't, the only thing that we really have to say is that the residuals are bigger for the quadratic. So the residuals that we computed are higher for the quadratic model. Right? The scatter plots don't tell, or we can't really determine much of a difference. So the scatter plots do not show a significant difference in distance between points and curves. The only thing I would suggest is more residuals are needed to make an informed decision. All right, so and that's what we're really looking for, is we're really looking at the scatter plots, and then we're also taking a look at seeing how much distance is in between. And like we said before, some of them have a lot of distance in linear, Some of them are almost right on the line. And then over here, it's the same thing with the quadratic. Okay, there's a couple of them, like these endpoints are almost right on there. This guy's pretty close, and then these guys, these three in the middle, are somewhat far away. All right, so it's difficult to make a conjecture without finding all of the residuals and then adding them up. What you'd probably want to do is you probably want to be able to find the R squared value or the correlation coefficient for both of these to be able to truly do that, to be able to truly make an informed decision. But in this class, we're not going to be able to do it except for linear types. Okay, so that's everything I think for this problem. And then the last topic that we have to cover in this section is the multiple linear types of regressions, which we're going to do in the next video.